I'd like to take some time here to evaluate a limit and look at it from a few different perspectives. So this is an idea that we're going to use a lot, where problems can be presented to us in a variety of ways. So the four ways that we're going to see problems presented to us in this class will be analytical, numerical, graphical, and verbal. And so I want to take a limit here and talk about what's meant by each of those and how we might approach a particular problem with each of those approaches. So the limit I want to do here is it has a function that let's just talk about that function here a little bit. You can see that it has an x minus 1 in the denominator. And if you remember from a pre-calculus class, when we get 0 in the denominator, we're going to see one of two things. Usually we're going to see a hole in the graph, or we're going to see a vertical asymptote. In this case, we're going to see a hole because we also have that x minus 1 in the numerator. So what happens here, if we try to evaluate this limit just by taking the 1 and putting it in where x is, what we get is 1 times 0 times negative 1 times negative 2 all over 0, which is 0 divided by 0. If you remember, 0 divided by 0 is indeterminate, and so we need to look at this problem from a different approach. Okay, 0 divided by 0 doesn't really give us an answer. So the first way I'm going to do this is I'm going to take values for x and I'm going to plug them into this expression, and I'm going to pick values for x that get closer and closer and closer to 1. So a few things that I want to point out here. First of all, when I say f of x in the table here, I'm referring to that function right there. When I plug in 1 itself, we get what we would expect, which is undefined because you can't divide by 0. So plugging 1 in, we get 0 in the denominator, and that doesn't work. However, it's really important that we remember that when we're looking at this limit as x approaches 1, x is not equal to 1. Okay, it's just going to be really close to 1. So what we do is picking values on the left of 1, getting closer and closer and closer to 1, we can see that the values we get out are getting closer and closer and closer to 2. And the same thing is happening on the right side of 1. So values that are bigger than 1, we plug in, and it's also approaching 2. So what that tells me is the two one-sided limits are both going to be 2, and so that means that this limit is going to be 2. All right, so when I say numerically, I'm talking about a problem where they give us information in a table that looks like this. And so numeric means that we just have values of a function at different points, and we'll have to answer questions based on those values. If we want to evaluate this graphically, I think this is pretty straightforward. We want to look at a graph of this function and see what that looks like. So if we graph this function, it has a really important feature here. You'll notice that it does have a hole at x equals 1. If you were to graph this on your graphing calculator, it's not going to show you that hole, or at least it probably won't show you that hole. So make sure that you understand that what you see on a graphing calculator, or even I graphed this in a program called Desmos. It didn't show me that hole. I had to put it there, but I knew it was there because of this x minus 1 in the denominator. So the function is not defined there. We shouldn't define it there in our graph. However, looking at this graph, we can see that as we approach from the left and as we approach from the right, the value of the function is approaching this hole, which is at the y value of 2, so we get the same answer. Okay, so we get that limit equal to 2. So both of these approaches so far are looking at the same function, but just from different perspectives. We plugged in values for x, we got values for y, and we were looking at particular points along that graph. So points that might look like this as we get closer and closer to the value of 1 along the x-axis. And those points were approaching 2. We didn't have to graph them, we could see that. And now we're looking at the actual graph. And so the graph gives us a little bit more information, a lot more information. It gives us those in-between points. But we can answer the question the same way. Now, analytically is just another way of saying algebraically. So we want to evaluate this algebraically. So I want to go back to this idea here that it doesn't matter what happens at x equals 1, it only matters what happens around x equals 1. And so we know that when we're evaluating this limit, x is not actually equal to 1. And what that allows us to do is actually cancel that term with that term. Or I should say that factor and that factor. So I can cancel those because if we did allow x to equal 1, we would be canceling a 0 and a 0, and we would be doing something really bad. You can't reduce a fraction by 0. That's not possible. But by saying that x is not equal to 1, it's just close to it, now we know that these are not 0. So that's not 0, that's not 0. So they can cancel with each other now. And by canceling, we have turned this limit into a simpler one. So those go away. So we have the expression x times x minus 2 times x minus 3. And I do want to point out, if we were to graph this function, it's what our graph looked like in this picture here if this hole was filled in. So all we did by canceling those x minus 1s is we removed that discontinuity. At this point, rather than looking at what's going on around x equals 1, since we've removed that discontinuity, essentially what we can do is say, okay, what's the value there? And we would get that analytically by plugging 1 in for x. So this is evaluating a limit by using direct substitution. So what that means is we're just going to take the 1 and plug it in for x, and we get 1 times negative 1 times negative 2, which is positive 2. Same answer we got by looking at the values in the table. Same answer we got by looking at the graph. The fourth representation that we might see doesn't really apply to this problem. So a verbal representation of a problem is just a description of, say, a function. So a problem might say a function goes through a certain point and it's increasing or things like that. So it's just going to be a description using words of what a function looks like. That doesn't apply to a problem like this, so it's not worth discussing here. But that is a fourth representation that we might see with problems in calculus.